Okay, this is effectively a talk about why I became an engineer and why after a quarter of a century I still absolutely love what I do, and I really get joy and satisfaction out of being an engineer and working for Arup. I'm going to use this word probably quite a lot during the talk, fundamental. Fundamental, in the context I'll use it, is the basis from which everything else develops. As Farah mentioned, I stumbled into engineering, and I'll be honest, I didn't actually know what civil engineering was when I turned up at Liverpool University back in the 80s. It was purely a vehicle to get out of Birmingham in the 80s. And if any of you have been to Birmingham in the 80s, you'll know why. However, something clicked when I arrived at university, and I discovered three really important things at university. The first of those things is that there seemed to be two ways to move through university, secure a degree. One was to study past papers and actually study to pass the exams. The other was to immerse yourself in the subjects and really start to understand the fundamental principles of what was being taught at university. And although this took more time initially, actually, if you understood the basic principles of what was being taught, you could then extrapolate that, and pretty much you could answer any exam question without revising the exam questions. The second thing I learned is engineering is an applied science, and those two parts are very important, the applied bit and the science bit. And it was the first time that I really got the connection between mathematics and all the things I was taught at school, calculus, algebra, geometry, and actually what they could produce. It was the first time there was a context to what I'd been taught earlier on in my life, and this really made a difference for me. And the third thing that I learned at university was there is a real artistry and beauty in solving an engineering problem to create something of real value and use out of that solution. This is a diagram I really liked at university. This is Moore's circle, and it looks incredibly complex, but actually it's a beautifully concise piece of maths that describes in one diagram and a few formula the stress and strain state within any solid object, so that you can work out the failure mechanism of that object, whether it's a piece of steel, concrete, soil, anything. It's an incredibly concise piece of maths and science, and really, really elegant, really, really beautiful. A lot of the applied science of engineering also creates things of aesthetic beauty. So shell structure, well-engineered shell structure is inherently beautiful as an object in its own right. However, some of the beauty, some of the artistry, I think is unseen, isn't necessarily associated with the aesthetic. We see some of the science behind the aesthetic, maybe in terms of proportion, the way things appear, the way things are juxtaposed, which has been derived based on science, but we miss an awful lot of the science. And I'll come on to this project a little bit later in the talk, because this is a good example of it. Historically, there was very little precedence, so people had to figure things out. People had to use reasoning, logic, and develop ideas and work out the fundamental notions that we now use in our everyday life. Archimedes in his eureka moment in his bath, figuring out the concept of buoyancy, which we all effectively take for granted now. Historically, there also appeared to me to be, at least within the intellectual classes, no conceived notion, or not the same conceived notion that we have today of profession. So, Da Vinci felt at liberty to be a philosopher, artist, astronomer, engineer, scientist, architect, and this is true in our profession in the building industry as well, dating right back to the first architect, which was Vitruvius, who was actually a soldier originally, and then became an architect. It's 2,000 years ago. Wrote his 10 books, De Architectura, which were effectively, the first codes of practice. He wasn't what we would recognise as an architect. He was a philosopher, master planner, engineer. One of his books of architecture, in Da Architectura, was purely about water, actually, and the use of water and the engineering behind that. So he's an environmental scientist as well as everything else. And I think this notion of master builder, I think, carried on until into the modern age as well, into the 20th century. This person is a guy called Pierluigi Nervi, who is a real inspiration of mine. He's an Italian, and he was a civil engineer also originally, but he was much, much more than that. He was an architect, he was a builder, he was a quantity surveyor, he was a material physicist. In 1930s Italy, to procure a project, you had to bid, like you would do now. You do an architectural competition, so you entered a design, but you also had to guarantee that you could build that design, and you had to guarantee at that conceptual stage the price of the design. So Nervi had to give a guaranteed maximum price for his design. So Nervi spent an awful lot of effort, time and effort, really refining the designs, making them economic as well as beautiful. And this is a diagram of a coffer slab that Nervi developed, which went into this building, the Gatti Wall Factory, outside of Rome, which uses also ferro cement. It's one of the first uses of ferro cement, which Nervi himself pioneered. So it's an incredible collection of skills and real insight. Over history, we've collected, an awful lot of information from the first book, 3000 BC, to modern times, where there's 130 million books in the world now. And the internet has made that wealth of knowledge, collective knowledge, even greater still. I'd like to pause for a moment. The first steelwork code in the UK came out in 1931. This isn't actually it. I couldn't find the 19. This is from 1943, but it was about this thin. However, before that code was produced, all of these buildings were completed. The Eiffel Tower, the Forth Rail Bridge, the Ritz in London, which was the first steel-framed structure in the UK, was constructed nearly 30 years before that code of practice. And these buildings were constructed by people effectively working from first principles, doing the maths, working things out, figuring things out for themselves. We move to modern times, and this is the code of practice that we have now, which is the equivalent of this code of practice. This is the Eurocode 3, which is the modern steel code. And I understand why we have codes of practice, but gravity is still the same. A lot of the principles behind it are still the same. So one question, Newton's apple still falls on his head. One of the things I'll pose then is whether we're being over-prescriptive in these codes of practice, and whether we're getting in the way, maybe, of creative design, creative development from first principles. Are we over-prescribing? As a complete aside, I'm average cook, I would say. I can follow a recipe, I can buy the ingredients, measure them out, make a decent meal. However, there's one thing I'll say I'm sublime at, is is a risotto. I cook amazing risotto. One of the reasons is someone bought me a book once by a guy called Giorgio Locatelli, who's a famous chef. He's got a place in London, absolutely brilliant chef. And I turned one day to the chapter on risotto, looking for a recipe, and there's no ingredients, there was nothing. It's just 7 pages of text talking about his childhood, talking about making a risotto, and talking about the 5 stages of a risotto. And I read that, and I thought, well, that's quite interesting. But actually, by the time I'd finished reading it, I can make any risotto imaginable. I don't need a recipe anymore to make a risotto. And I found actually a lot of the existing recipes missed out some of these important stages. It was a fascinating read, but it liberated me to not need a recipe to make a risotto. I want to make it clear that I'm not talking about reinventing the wheel here. I think it's a incredibly negative connotation associated with reinventing the wheel. I think what I'm always referring to here, I think, is developing the wheel. And I think we should stop using the term "don't reinvent the wheel." I think we should turn that around and actually use the term "continue to develop the wheel." This is I guess the latest development in wheel technology, which is the Vegas Flyout, which is an Arup project, which is, I guess, moved the wheel on from its wagon wheel days quite considerably. But it's an incredible piece of engineering. So there's all this data in the world, there's all this information, there's all this precedents, there's these codes of practice. I'm not saying that's a bad thing, actually. I'm saying that's good. I think it's the way you use it that you have to think about. This is a project we're doing with Jean Nouvel in Qatar. It's a museum building. It's 50,000 square meters. It's under construction at the moment. It's on the Corniche in Qatar, and it's based on the concept of the Desert Rose, which is a naturally forming sand sculpture. There's not a single straight line in the whole building. The rooms are made by these intersecting plates. Every time you move a plate, the whole building, it's like a butterfly flapping its wings. The whole building changes, all the geometry changes. Our concept design for this building, it wasn't a single drawing, was actually an algorithm and a series of scripts and a process. So we described at concept design the process of how we could engineer this building, how we could manage all of this massive wealth of data and turn this data into a final construction. So the concept here was an algorithm and a script and a process. Moving on to some other examples. This is CCTV which is China State Television headquarters building in Beijing. It's a new headquarters building we completed with Rem Koolhaas in Beijing, and a project, probably my favourite project in the last 25 years. One of the reasons it's my favourite project is in China, if you design a building to the code of practice, you're absolved as an engineer of all responsibility. If your building falls down, you're not liable. The state takes liability. If you can prove that you did everything that was in this code of practice, you're not liable. The code is liable. However, that means the codes are very, very prescriptive, and this building breaks about every single rule in the code, and probably everything you would sensibly do in a major seismic zone. However, that's not the end of it. If you break the rules, what the Chinese government do is they appoint 12 specialists who become the code of practice. And then you spend however long it takes persuading these people or not that you can build and you can design, build this building, and it's safe. And for this project, it was incredible. I mean, it's another talk in its own right, but it was an incredibly protracted process of convincing these people, because these people take on liability. These people take on the liability of the code of practice. And the extremities, we did everything. We made computer simulations of the building. We made tests of pieces of the building. We even made a 1:40 model of the whole building, put it on a shake table test in China, and shook it to the maximum earthquake it was going to see, just to test that. And to test it worked, but also to convince the Chinese expert panel that this was a safe building to construct. And this was the final product. On a slightly smaller scale, this is a building or a project, piece of project architecture that we did with Carmody Grok, a brilliantly talented young practice here in London. And the essence of this design is the slenderness of these 250 steel columns, stainless steel columns. This is on Euston Road, Osnaburg Street, and I implore that you go and see it at some stage. It's very close to here. A beautiful piece of architecture. But for it to be beautiful, these columns had to be this slender. They're 8 meters tall, and they had to be 50 millimeters by 50 millimeters. Any more, and the elegance and beauty diminished significantly. Precedents and the code of practice, and actually the client's engineer as well, told us these couldn't be this size. They had to be at least 100 millimeters, which would have killed the whole concept. So we said, well, we don't believe that. Actually, what we'll do is we'll approach this completely from first principles. Right down to, we even invented the loading criteria for this, because the code of practice, there's no loading criteria that's suitable for this. So we invented the concept of a hoodie load, which was how many hoodies it would take to either shake it to pieces, buckle it, pull it apart. And actually, this is a submission. This is a page from the building control calculations that we submitted, which at first they thought was a bit strange, but actually they thought it was fantastic in the end, because we'd really thought, I think they got the fact that we'd really thought about how this building would behave and what the real criteria, performance criteria, should be for this building. One thing we found when we were doing this project is actually under our hoodie load, the code of practice actually was unconservative in one respect. It assumed that there was too much damping inherent in the structure. And actually we found by doing a test, a full mock-up test, that one of these hoodies, if they could hit, after however many pints, could hit the resonant frequency of the structure, they could shake it to pieces. So, vibrating one of these columns, they could actually shake it to pieces. And the code had got that wrong. So we found this phenomenon out, and to deal with it, engineered, I think, an incredibly elegant solution, actually, which you don't see, and that's the whole point. It doesn't detract from the beauty of the architecture. But there's a stainless steel rod in each one of these 250 columns in a neoprene sleeve that just very gently bangs against the side of each one of these columns when it's being shaken. And it damps out all of the hoodie energy that gets generated. So an incredibly elegant solution, but one nobody will ever see, nobody will ever notice. And I don't think that's a problem, but sometimes some of the beauty of an object is implicit, I guess, rather than explicit. And as I say, I implore you to go and see it. It's a beautiful piece of architectural sculpture. Now this, on the other hand, is probably the ugliest building I've ever worked on. Yet, I think it's one of the best pieces of discrete engineering that I've been involved in. It's in Taiwan, in Taipei, and it's a steel frame building in a major seismic region. The big difference is in the top of all of the braces, we've inserted this comb-like device, which is basically just a series of steel plates, triangular steel plates, inserted into the top of the brace. And what that does is when the earthquake happens, if you've ever taken a paper clip and bent it backwards and forwards really fast, you can find it gets hot, actually, and that's the paper clip dissipating energy. And these things work on exactly the same principle, exactly the same fundamental principle. When the earthquake hits this building, the only bit that gets damaged are these little steel plates, and they cost $1,000 each. There's a couple of hundred of them, and they saved an absolute fortune in terms of the steelwork in the rest of the building. And we could engineer them in such a way that the steel fabricator could build them. So the same steel fabricator who built the steel frame of the building built these devices. It's a brilliant piece of. I think challenging precedents doesn't always have to be about adding something. I think sometimes it can be about not doing something. So, sorry, this is the V&A, Medieval and Renaissance Gallery. And the clever thing we did here was, this is a chart showing relative humidity versus temperature. And actually, ordinarily, gallery space is conditioned to a very, very tight zone in that chart. And we worked out through a lot of exploration, a lot of talking to the curators, etc., that we didn't need to control the temperature, actually. What we needed to control was just the humidity, and we could let the temperature range well outside of that zone and saved an absolute fortune in terms of the operational energy used to condition that space, and actually made it a more pleasant space to visit. I mean, a lot of what's in that, should be in a fairly external environment anyway. I thought that was a brilliant piece of first principles thinking, and a really valuable one as well. I have a project that we're looking at in Berlin at the moment, and in facade engineering there's a paradox, I guess. We want to let in as much daylight into our buildings as possible, but facade engineers and designers wrestle with keeping the solar energy of the sun out. So there's these two things conflicting with each other. I thought this is what we're proposing for a project in Berlin at the moment, and it's electrochromatic glass, which deals with the kind of fundamental of that problem. So when the sun is directly shining on the glass, electric current blocks it out. As soon as the sun's gone, electric current goes, and you've got your view back. And I thought it's a brilliantly simple idea, and I guess will hopefully lead to some really, really good pieces of architecture, pieces of facade design. Extrapolating from that point, this is a project our Berlin facade team are doing, BIQ. It's a demonstration project in Germany. And actually, here, this doesn't look great. The notion or the idea is taken even further, and actually, can you use that sun's energy can you harvest it? Can you block out the sun, but also harvest that energy? So this is an experimental project with growing algae in a facade. So the sun shines, the algae grows, it blocks out the solar energy. Sun doesn't shine, the algae dies. You then put it in a bioreactor and harvest that energy. I don't know. I think it's great. This is about developing the wheel, pushing things on. I don't know whether this will have legs as an idea or not, but it possibly will lead to something else. Because I guess these guys, in their magnificent men in their flying machines, didn't know that this was going to lead to this. And I think that's why you have to keep pushing ideas developing thinking, you know, referring back to the first principles of what you're trying to achieve. One of the reasons this is important, and I think this is a great statistic I picked up from, I think it was Brian Cox's show, which is the UK represents 1% of the world's population. It produces 3% of the GDP of the world, but actually it produces 15% of the peer-reviewed scientific papers that are produced, which I think is an incredible statistic, actually. It really shows, in terms of science and engineering, as a nation, we punch massively above our weight. And I think we have to continue to do that, because this is an example of what happens if you don't. It's the Morris Minor, I think. But, I mean, it's beautiful to look at, and it's a lovely piece of nostalgia. But, you know, there's only so much nostalgia you can live with. I think you have to keep pushing the development of the wheel. So, I think in summary, I love being an engineer and working for Arup, because it allows me to continue to creatively question and push out precedents. It allows me to continue to develop the wheel. And from that, I get amazing joy and delight. And this is why, after a quarter of a century, I still love being an engineer and still love working for Arup. And hopefully we'll continue to do so. And I think this was a nice quote that I picked up from, it's actually an advertising executive, but I think it applies here. Applies here anyway. Principles endure, formulas don't. That's the end of my talk. Thank you very much.
Chris is fantastic. To me, Chris is the man. I mean, he's an engineer's engineer. I've been working with Chris on several projects for several years now at Zaha Hadid Architects. We worked on the National Art Museum of China competition. We worked on what is now the Tokyo Olympic Stadium competition, which we won. And we are looking forward to doing more projects with Chris and in Arup in general. So it's been a very productive relationship, and we look forward to doing more.
I think it was a wonderful balance between sort of the pragmatics of the discipline and with it a lot of what is the joy of working with Arups. You know, it's fun making things work, and I think particularly the hoodie element of putting the sculpture together and actually digging in deep and finding more to the parameters and problems than was first evident. That was absolutely fabulous.
I think what's lovely is to hear an engineer challenge, and probably as a client, to challenge the client, because innovation needs clients that are forward-thinking and are prepared to not accept the status quo, but, I think in Chris's words, to continue the evolution of the wheel. So I think fascinating stuff.
I thought it was fantastic, and to see somebody so enthusiastic about maths was absolutely brilliant. I just wish he'd explained the diagram so I could have an equal understanding as well. But no, fantastic talk, really inspirational.